Let's begin today with something, um, and I would say more theoretical than what we've been doing so far. So we've been doing a lot of probability. Particularly, we've been dealing with conditional probability, and we used heavily Bayes formula the past two lectures. So Bayes formula is now our new bread and butter. So we've been after finding, calculating, computing the probabilities of an event occurring. So we've been, I think, much better with what probability is and how to compute it. And now we're going to be heading into more of the theoretical aspect of probability. And it has to deal with what's called a random variable. So we're going to be talking about what are called random variables. Now, this will become our new topic of interest related to probability. I remember when I was a student myself and I was learning this for the first time, I had no idea what this meant. No idea. So random variables, it sounds a bit misleading with the word variable. But a random variable is a function. So a random variable, we can define it to be is a function that is defined on the sample space of a probability experiment. So that's the way we're going to start with this. Okay, we have to remember what functions are. So functions are rules that assign an input to an output. And it's really an input to one and only one output. That's what functions are, right? So now we're utilizing that same concept of a function, but now we're applying it to probability experiments. And we already know that probability experiments have what are called sample spaces. And sample spaces consist of all the outcomes possible of this probability experiment. In a sense, we've been dealing with random variables up to this point without actually saying that we're dealing with random variables. But now we're explicitly saying we're going to be dealing with random variables. Now, normally we denote random variables with uppercase letters. So it's normally it is common. So note, we commonly use uppercase letters such as X. I'm using a uppercase X, not a lowercase x, such as X. And usually it's kind of noted this way. We commonly use uppercase letters such as X to denote random variables. Of course, this sounds very, in a sense, abstract, because how do you define a function on a sample space? We are accustomed to having a number, for example, as an input to a function, and we get a number out. But in this case, our function has a outcome of a sample space as the input, and the output is a number. So I'll write that down. So our random variable, the input of random variable is, I should say equals, an outcome from the sample space. And the output of a random variable is simply a number. And I would just call it a real number. So what we're doing is we're assigning numbers to outcomes. Okay, and that assignment of a number to an outcome depends upon the probability experiment itself. Okay. For more of a pictorial view of this, right? So this is more of a using a machine diagram for functions. We can think of it as have some kind of conveyor belt here. I'm going in this direction, and the input is something in the some outcome. In sample space. I put it into this function called a random variable called x, and then the output is a number. And now what's cool about random variables is that you are able to almost create one every time in a creative fashion. It's not so rigid. It's not so rigidly defined. So let's look at an example, and we've been dealing with this example a lot, but it's a good illustration. So an example, consider the probability experiment. The probability experiment of rolling 2 dice. We've seen this several times now, and I hope everyone has an immediate reaction, a good reaction to it, and know exactly what I'm going to go with this. The sample space, I hope everyone remembers, can be viewed as a grid of numbers, of pairings of numbers. And the first coordinate here you can say is what the first dice rolls, and the second coordinate is what the second dice rolls. And then we have a space of outcomes, correct? And I hope we already know where this is headed with all the outcomes. And there's a total. I'm gonna write a few more actually. So this is 2, 1, this is 2, 2, this is 2, 3, this is 3, 1, and then so on and so forth, right? We've seen this diagram before. So this is 36 outcomes, right? A total of 36 outcomes. 6 by 6. Now, the cool thing, what I can do is I can create what's called a random variable. So let's create one. So there's a lot of these let statements, right, that we've been able to do over the course of the problems where we use a variable. We use a letter to define a set. And I want to use a capital letter to define not just a set, but it's a random variable. So let x be a random variable. That is defined as the sum of two fair dice, of the two. So you may think we already did this the first time we talked about this illustration of rolling two dice, this example. We already did it. We already did it, right? When we defined the probabilities of finding the sum, but now we're explicitly defining it as a random variable. And once I do that, then what are the possibilities for the value of this random variable? So the random variable, what's the possible all possible outputs of X? So what are all the possible outputs of X? What could this random variable X actually be? Again, I know it's a little strange to talk about this. We normally use variable X's, small x's with variables. But now we're dealing with the capital letter X, and that capital letter X represents a function that's defined on a sample space whose outputs are real numbers. I know that it may sound a little strange because it did to me as well. I didn't understand it at first. I'm like, what are we dealing with variables, yet they're called functions, yet they're called random variables. So if I define my random variable as a sum of two fair dice, what are the possible outputs? What are the values that this random variable can be? So what are the sums? What are different sums? So 36 is the number of outputs. Very good. So Hijab and Daisy, very good. That's exactly right. So X, this sum, instead of now, you understand what we do in mathematics? We use words and then we just make them into a symbol. So every single time we say, hey, what's the sum of the two fair dice? Instead of saying this, every time we're saying, what is X equal to? Which represents the random variable defined as the sum of the two fair dice. So X, right? X could be what? It could be 2. The random variable can equal 3. The random variable can equal 4. The random variable could equal 5. The random variable can equal 6. The random variable can equal 7. The random variable can equal 8. The random variable can equal 9. Then it goes all the way to what? 10 and 11, right? So maybe I should write this. X equals 6, 7, 8, 10, 11, and then finally 12. So do you see what we're doing? It may seem like we're not doing much, but what we're doing is we're organizing our possibilities, right? All of our outcomes of rolling two die. We're now creating a way to, and we're organizing it in reference to the sum of those two dice. So we're, instead of doing the whole picture and then we use these, like we usually create like little circles, ovals, and we group those outcomes together and say, hey, that equals a certain number. Instead of doing that, we're using a more systematic way of doing so. So for example, X equals 2 is the result of rolling two fair dice and the sum of it being a 2. So we're not so concerned so much so with just what the random variables equal. What we actually care about a little bit more is what's the probability of this random variable attaining the value of 2. So again, we've done this already, but now we're giving it more of an algebraic flavor to it. So instead of saying, hey, what's the probability of rolling two fair dice so that the sum of it equals 2, I'm saying, hey, let's define X uppercase to be the sum of the two fair dice. And then we're saying, hey, what's the probability that X equals 2? Do you guys see what I'm saying? So the probability that X equals 2 is meaning that what's the probability that I roll two fair dice, and that sum equals 2. Well, the only possibility, the only way that happens is if we get 1, 1. And that's 1 out of 36. So this is 1 out of 36. So what I'm introducing really is more notation of a more theoretical framework applied to probability than we've done so far. So far, we've just been dealing with problems, breaking that down slightly into events, and then finding the probabilities of those events occurring. But now we're like looking at it from a much more broader perspective. And then the same thing goes here, right? What's the probability that x equals 3? Yes, Mir.
Shouldn't it be since it's one outcome out of a total of 11 outcomes, shouldn't it be 1 over 11?
Okay, very good question. Very good question. Again, what's the underlying probability experiment? It's the rolling of 2 fair dice. That's the underlying probability experiment. So we actually have 36 outcomes. What we're doing is now we're taking these 36 outcomes and we're applying upon it a way to organize or to divide up this sample space. We're saying, hey, you know what? Given this probability experiment of rolling 2 fair dice, I want to create what's called a random variable that tells me something about the outcomes, all of the outcomes of this probability experiment. So we're saying, you know what? Let me define the sum of the 2 fair dice to become what's called a random variable. So in this probability experiment, I'm defining a particular way of a particular interest that I have in this probability experiment. I care about the sum of the 2 fair dice. So do you see how this here? I care about this sum, but does it have to be the sum? Could I just say, hey, I want to know what's the product of the 2 fair dice? Or I want to know what's the quotient of the 2 fair dice? Or I can create something else. It doesn't have to be a sum. Do you understand what we're doing now? We're talking about something broader. This is a particular example of a random variable that we've already discussed when we first talked about this probability experiment. What I'm showing you guys is that this random variable can be defined in more than one way. The way we interpret or the way we are interested in this probability experiment can be from different angles. Some people care about the sum of the fair 2 dice, but do we always care about the sum? Is that the most interesting thing in the world? No, we can also talk about the product, for example, and that's a new random variable. The number of outcomes doesn't change of the probability experiment. That's consistent, that's unchanging. What changes though is the random variable that we define. And what changes with respect to the random variable that we define are the values of the random variable. So the moment I say, hey, I care about the sum of the fair 2 dice, then the next question is, what are the different sums for the 2 fair dice? What are the different sums? Well, the sums can equal 2 because 1, 1, right? Equals 2. The sum can equal 3 because why? We have 2, 1, right? And 1, 2. So then this here, these 2 outcomes become part of the random variable when it equals 3. And so then now this becomes what? 2 over 36. It's not over 11. Because the random variable attains 11 different values, it does not mean it has 11 different outcomes. Again, I know this is a little strange, but you'll see eventually why this is actually very, very applicable and very helpful to define random variables. Yes, Mir.
So does it make sense to say that the reason it's not over 11 is because each of these values has a different probability of occurring?
And yes, and they have a different probabilities of occurring because each of these random variables have different sets, different outcomes that are associated with that value of the random variable. For example, what's associated with x equaling 2? What outcome is associated with that? The only outcome that we have is 1, comma 1. That's associated with the random variable equaling 2, meaning that the sum of the fair two dice equals 2. Now, which outcomes are associated with the random variable equaling 3? Then we got 1, 2, and 2, comma 1, right? These two are associated with the random variable x, which is defined as the sum of the fair two dice, equaling 3. And then so on and so forth. Then we have, what's the probability that my random variable that I defined equals a 4? Well, then I have what? I got 3, comma 1. I got 1, comma 3. I got 2, comma 2. These three outcomes are associated with the random variable x equaling 4. Does that make more sense now? And now this will equal what? The probability that this equals a 4 depends upon these three outcomes occurring. So these three outcomes each have equal probabilities of occurring. 1 out of 36. So we have 3 out of 36, and so on and so forth. Yeah, the sample space. Yeah, so the sample space, of course, changes when we talk about a completely different experiment, probability experiment, which would be 52 card deck is another typical probability experiment that we deal with. But that's the way this goes now, guys. This is what we're going to be considering now. What's the probability that a random variable that we define equals a certain number? And then this keeps on going, right? So we have 5, 6, right? Probability x equals 7, probability that x equals 8, the probability that x equals 9, the probability that a random variable is 10, and so on. Okay. So then so we increment by ones every single time. We have one more additional outcome that's associated with our random variables as we head to x equals 7, I believe is, yeah, x equals 7 has the most outcomes associated with it. It has 7 out of 36. This has 4 out of 36. This is 5 out of 36. And then this decreases again, right? We've seen this already. 12. Sorry, this should be 6, 5, 4, 3. Yeah, pardon me. This should be 6. This should be 6, and this should be 5. There's only 6 outcomes on the diagonal of a 6 by 6 grid. So yeah, it should be 5, 4, 3, 2, 1. It should be symmetric because of the symmetry behind the outcome. So now we have a random variable that we defined, and we know the probabilities of each, the probability that our random variable equals the particular numbers for each. So with this now, we can see what? We can see that if we take the sum, so look at the notation here. If we take the probability and the union of the sets of the different possibilities, right? So x can equal certain numbers. And what are those numbers? The smallest value for our random variable is a 2, and it goes all the way to 12. And now you start to see, right, that I'm dividing up my sample space into these different groups of outcomes. So one group has a sum of 2. Another group of outcomes have a sum of 3. Another group has a sum of 4, so on and so forth. So what did I just create? I created a way, in a sense, partitioned the sample space by the sum of the two fair dice. Because I partitioned it, these random variables are associated with outcomes that are mutually exclusive from one another. You can't have this outcome equaling a 4 when you add up the sum, and it also equals a 3. So you can't have these. So because of that, right, we can now find the probabilities, and if you sum up the probabilities, as you can clearly see, what should be the sum of the probabilities when you add them up? Well, these are the only possibilities of the sum equaling a number, right? You only have all, we've defined all of them, and there's no more, and there's no less. So the probabilities when you add these all up should give you what? 36 out of 36, which is 1, which makes sense because each of these, when you put all of these random variables together and you union them, you're representing the whole sample space. And we know that the probability of the sample space is 1. So we're saying something that we should already have imagined and thought of. So the probability of the sample space, and the sample space is defined by the union of these random variables. So any questions about random variables? Or at least this example with the random variable. Maybe random variables are still a little bit confusing, but we're just revisiting a topic that we already dealt with, but now we're putting on a more theoretical idea. Okay, so those are random variables with respect to this rolling of 2 fair dice. Okay, so what we found in what we found here with all these probabilities are called what are called a probability mass function. So you see, all of this stuff just sounds more theoretical. So the probability mass function is the probability, simply what we just found. It's the probability that a random variable equals a certain number. That's what the probability function is. It's the probability of the random variable attaining the value of n, where n is a real number. So for every single time we found these probabilities, we're finding the probability of the random variable attaining a certain number. So then we call this P of n. So when we say P of n, we're really saying the probability that our random variable equals n. And you see there's a lot of equal signs now, like there's a whole bunch of equal signs, but just be careful where the equal signs are. The equal signs inside here are with respect to the random variable, and the outside one is related to the probability of the random variable equaling n. Okay? Okay. So with that, let's discuss what are called discrete. So examples of discrete. Examples of discrete random variables. So we'll be discussing 2 kinds. We'll be discussing 2 general categories of random variables. We'll be dealing with discrete random variables, and there's several different types of those. And then we have continuous random variables, and we have different types of those. So for those of you who have ever taken probability before or statistics before, you probably have heard of the standard bell curve. Who has heard about the standard bell curve, right? That's considered what's called that's considered a normal distribution. That's a normal random variable, but no one talks about it that way most of the time, right? They just say, hey, it's the standard bell curve because it looks like a bell when you draw it. But it's precisely what's called a normal random variable, and that normal random variable is representing a continuous random variable. So we'll talk about that later, but I'm just giving you an idea of what random variables may look like. And you've seen them already, but they don't really talk about it in that light so much in general. But now we're going to be talking about, for now, discrete. So the difference, so does anybody know what's the difference between discrete and continuous? I know some of you are computer science majors and have taken discrete math. So what makes discrete discrete and different from continuous? So someone says no gap. Daisy says no gap. Okay, that's, I can see why you say no gap. No gap is continuous. So without using the word continuous, yeah, that's kind of okay. No gap means continuous. Discrete can be broken down to finite elements. Now that's a very interesting word, finite. What does it mean? What does it mean something to be finite? So discrete can't be infinite? Can't be continuously broken down to smaller pieces. So again, my question is, can discrete, when we talk about something that's discrete, can it be infinite or does it have to be finite? Cannot be infinite, I think. It's finite. So discrete, I know people think of no gaps, which is fine. People think about, you can break it down to smaller pieces. That's, or you can break things down on discrete, but you can't break things down in continuous. Is that what you're saying? That's one way, probably, yes. But discrete has everything to do with what are called the natural numbers or the counting numbers. So the counting numbers, right, are what? 1, 2, 3, 4, 5. And it goes on to infinity. So without getting too crazy with this, there's different types of infinities. You can categorize infinity as two different things. It could be either countably infinite, or something can be what's called uncountably infinite. So discrete really deals with the natural numbers only. So for example, what's discrete? If you can count it with counting numbers, it's discrete. If you can't count it with counting numbers, it's not discrete. And most likely it will be continuous. So when something is continuous, you can't really use the counting numbers. So for example, when you want to find so uncountably infinite is not discrete. It's the antithesis of being discrete. If you're uncountably infinite, for example, the real numbers. If you're on the number line between 0 and 1 and you want to count all the numbers between 0 and 1, good luck. You can never do that. If you count all the real numbers between 0 and 1, that's an example of what's called being uncountably infinite. But if you want to count all the real numbers between 0 and 1, but for example, if you want to count all of the rational numbers between 0 and 1, so all of the numbers that can be expressed as fractions, that's actually countably infinite. You can actually count those, and that would be something that's discrete. So discrete are things that you can count with the natural numbers. Being continuous, you can't count with the natural numbers. So that's why when we talk about discrete math, you're talking about counting. You can count them with 1, 2, 3, 4, 5. Of course, it gets more complicated. We talked about it, right? Different ways of counting. You see, they're all whole numbers and they're all positive whole numbers. They're counting numbers. We don't have fractions. We don't have numbers with decimals and unending decimal expansion. We don't have irrational numbers. That doesn't even come into play at all here. So that's one way to distinguish between discrete and non-discrete, or continuous. So I'll give you the first type, the simplest kind of discrete random variable, and that is the so type number 1. This is called the binomial, pardon me, the Bernoulli, after the mathematician Bernoulli. Bernoulli random variable. That's the first kind. And the Bernoulli random variable has a very simple structure. So suppose a trial. So remember, we talked about experiments. We usually use the word trial or experiment to represent a problem in probability. So suppose a trial or experiment has outcomes classified as either a quote-unquote success or a quote-unquote failure. Then we define our random variable as the following. So you see here, in a way, this almost seems arbitrary, but this is how Bernoulli defined. He just says either x equals 0 or x equals 1. And this occurs when the outcome is what's called a success, when the outcome is a success, quote unquote. And when, oh no, pardon me, that's the other way around. Usually we use 0 for failure. So when it's a failure and when the outcome is a success. So actually we can consider this as like a piecewise function. So consider as piecewise function. For those of you who don't remember what that is, hopefully you see this example. So x, right, could be either 0 or 1. But when is it? What if outcome is success? Or if the outcome is a failure? So you see here, our random variable that we defined, we kind of, in a sense, arbitrarily gave them these two numbers. We could have given it any numbers for the outcome being success or failure. Sorry, it should be the other way around. It's 1, 0. Yeah, I just saw. I just usually 1, 0, 0, 1. The idea is when you have an outcome being what's called a failure, we say x equals 0. When you have the outcome being success, we call it we say x equals 1. And what kind of probability experiment exists with this? So an example of a Bernoulli random variable. So think of any probability experiment that only has 2 outcomes. So this random variable is a way to explain every probability experiment that only has 2 outcomes. So can anyone think of a probability experiment that we discussed before that only has 2 outcomes? Flipping a coin. Exactly. See, you guys got it. That's right. So when we flip a coin, we're representing that as a Bernoulli random variable. So do you see how, in a sense, what we're doing? We're generalizing the experiment of flipping a coin as some idea of either having a success or failure. And now the way you define, that's why we put it in parentheses. What is success and what is failure? This is just one way of, with words, explaining an experiment that has only two outcomes, a binary outcome. So you can say, hey, you know what? Let me flip a coin and let me make the success being that it flips on heads. And if that's the success, then the failure would be it's on tails. So then, and I could have flipped it. I could have switched it as well. I could say the success. Let's make success be the outcome of flipping a coin to be tails instead, and the failure of it being heads. The idea is that it doesn't really matter what's a success and what's a failure, as long as when you do define the success, you're consistent with what the failure would be, and it's just two outcomes. That's really it. So we can say, hey, let x be the random variable for flipping a coin, flipping a two-sided fair coin. And let x equal 1 if coin flip lands on heads, and 0 if coin flip lands on tails. So that's the way we define it. And then when we want to find the probability mass function, and we also use we denote or abbreviate, the abbreviation to this is PMF, because it starts with PM and F, right? So the PMF, what's the PMF of this random variable? Well, this random variable can either equal a 0, or this probability can equal a 1. Again, this is the probability that my random variable equals 0, the probability that my random variable equals 1, which means that the probability that it lands on heads. Sorry, lands on tails. Or the probability that it lands on heads. And obviously it's 1/2, 1/2. You guys see that? So the idea that we're doing with random variables is, instead of writing words, we're using letters with numbers. That's really what we're doing now. And that's what we do a lot in mathematics. We want our words to not always have to represent our events with all this long English, right? We want to find a way to generalize this to all possible, in this case, all probability experiments that only have two outcomes. We can just say, hey, you know what? Like, let's make one of them equal 0 and make the other one equal 1. So we don't have to do this anymore. We don't have to deal with this anymore. The moment we define it this way, now it's just quicker to represent it. Makes sense so far with the probability experiment of Bernoulli random variable? And this is the simplest one. There's only two outcomes. So once we understand this, and so once we have this, then we can talk about the next kind of random variable. So we talked about type 1, right? Bernoulli. Now we're going to talk about the second type. And that's called the binomial. And this one is very important because this comes up a lot. This is a common one. So what is the binomial? The binomial random variable. Okay, so it piggybacks off of the Bernoulli random variable. So let me just take it. So the only difference, you can talk about the binomial random variable being like an extension. This is an extension of Bernoulli. Now, what's the difference between the binomial and the random variable and the Bernoulli? The Bernoulli is when you have an experiment and you perform the experiment only once, right? You either flip a coin and you do that one time and that's it. So that's the main difference. So suppose the Bernoulli random variable, I should say, occurs for probabilities for experiments only performed once. So if I flip a coin one time and I stop, that's it. There's no more. That's representing a Bernoulli random variable. But what happens if I don't want to just consider a probability experiment and it only being performed once? What if I want to do it 3 times, 5 times, 10 times, 1,000,000 times? You see my point? With that, we have what's called a binomial random variable. So it's really a Bernoulli. It's just that I'm applying it n number of times. So when an experiment, when a probability, I should say, when a probability experiment is performed n number of times, and what we say is that when we perform it, they're independent of one another, and the trials are independent. So if I flip a coin, for example, the first time I flip it does not affect the second time I flip it, and so on. So when we have experiments whose outcome, when you perform it, does not affect the next time you perform it, right? They're independent. We have what's called a binomial random variable. So when a probability is performed and the trials are independent, with each trial having only 2 outcomes, we have the following. So again, we have this outcome, right? So my variable x, my random variable x can either be 0 or it could be 1, right? A success or a failure. But now our random variable is defined a bit differently, actually. So let me just show you what I'm trying to say. So if, for example, my random variable is I, this tells me I want to know what's the probability of having a success I times when an experiment is performed n number of times. So now we care about how many successes what's the probability of having a success I times? So when is the random variable x is defined as the number of successes given the n number of times that I perform my experiment. Does that make sense? So for example, we've done this before. So recall again, right? So revisit flipping a coin. Flipping a coin experiment. Now, suppose I do this 8 times. So suppose I flip a coin 8 times. You see how when I flip it 8 times, each time it's independent of the other times that I flip it. And when I flip every single time, every single instance of me flipping that coin, I only have 2 outcomes, heads or tails. Now, what are the values of my random variable? Again, my random variable is a binomial random variable. So what are the outcomes of my random variable? What are the values of my random variable? So let me just define what x would be. Let x be equal to the number of times that a coin lands on heads after being flipped 8 times. Bang, you're correct. A daisy. So how many times can I flip a coin? Heads, being heads 8 times. So my heads here, I'm considering that as my quote unquote success. So immediately, what's my failure? Tails, right? Immediately. But what I'm doing is I'm only looking at my probability experiment with the lens that success is heads. How many heads do I have when I flip 8 times? So I can have what? X being 0. I can have no heads, right? So this represents no heads. What does x equal 1 represent? 1 head. So on and so forth, right? X equals 2. 2 heads. All the way down to what? X equals 8. All heads, right? And if I have no heads, then I have what? What's associated with having no heads? I got 8 tails. If I have 1 head, what's associated with that? I have 7 tails. If I have 2 heads, then I got 6 tails. So on and so forth, right? If I have 8 heads, then I have 0 tails. So far, so good. Does that make sense? So my random variable is defined by the number of heads that I have in 8 flipping of coins. Now, associated with each of these random values of random variables, I'm concerned with, for example, what's the probability of that occurring? So, example, what's the probability that x equals 3? What's the probability that I have 3 heads out of the 8 times that I flip it? So how do you think we approach that? So do you see how we have to think about this? What if I have these 8 slots that represent the times that I flip the coin? So 1, 2, 3, 4, 5, 6, 7, 8. Now 1 8. So hold on 1 second there, Mir. 3 8s. So what is associated? Think about what outcomes are associated with the random variable equaling 3. What does this mean again? This represents that I have 3 heads out of 8, right? So then some people say 3/8, some people say an eighth. So I want to know how many ways, how many outcomes have 3 heads with 5 tails. So for example, I can have this: heads, 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 tails, 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 correct? Now the question would be, is that the only way to get 3 heads and 5 tails? And the answer would be no. How else can I get this? I can have heads, tails, heads, tails, heads, tails, tails, tails. That's another way. How else can I get this? Do you see how this now becomes more taxing? Because actually there's many ways. You can have tails first, then all heads at the back. Then you can have an assortment of different arrangements. Wait a minute. Arrangements. So there's a lot of different comments here all of a sudden. It's good. Permutations and then find a probability. Yeah, so you're there. You're there, Alexandra. Christian says 3 factorial over 8 factorial. I know, because you're dealing with the 3s and the 8s. You want to deal something with the 3s and the 8s. But 3 factorial over 8 factorial, you have to understand also where those numbers come from. Why 3 factorial? What does that represent? And why did 8 factorial? And Ethan says 8 choose 3. Huh. So Ethan, why do you say 8 choose 3? Eight positions for 3 heads. Right. That is right. So I hope you start to see how counting is fundamental in this whole probability theory. What I could do is I can go through every single possible arrangement of 3 heads among the 8 positions. I can do that, but it's going to take a long time. And I don't really care so much about what the particular arrangement of the letters are. I care about how many are there. So I care about the number. I care about the number of ways that 3 heads appear out of the 8 flips. And so in order to count all of that, I have to do the following. And this is what we've done with counting, right? With combinations in particular, the binomial coefficient. I don't know if I think we discussed it that way as well. If I want to figure out the number of ways that 3 heads appear out of 8 flips, it's the same thing as saying, hey, out of the 8 slots that I have, choose 3 of them to be heads. I just want 3 of them. So how many ways is that? 8 choose 3. There's 8 choose 3 ways of selecting 3 of those positions, slots, to be heads. This is one way, right? The first 3 are heads. This is another way where the 3s are one after the other, but they're off by 1, right? All the heads are at the end. And then all the heads could be within the flipping of the coins. So 8 choose 3 will give me precisely the number of ways that I can select 3 of the slots being heads. Now, what's the probability, for example, that the first outcome here occurs? What's that probability? Does anybody see what I'm asking? What's the probability that this whole thing occurs? Does anybody know? Mm, should be one out of the total outcomes. So think about it this way. What's the probability of me, of my coin being ahead? It's 1/2, isn't it? The probability of that I get another head, 1/2. The probability of me getting another head, 1/2. The probability of me getting a tail, 1/2. The probability of me getting a tail, 1/2, so on and so forth. So the probability that this first outcome occurs is not 1 out of the total. The probability of this occurring is that I have 1/2. Whoops, sorry about that. 1/2 raised to the 8th power. And then what happens with this one? What's the probability of this event occurring? So you see how this is a little bit different than the other problems that we've done with the rolling of the fair 2 dice. Because we were able to enumerate all the outcomes when you roll 2 dice, which is 36, it was easy to say, oh, it's 1 out of the many. But here we haven't enumerated all of them. If you really want to enumerate all of them, this would be for every position, there's 2 outcomes. There's 2 to the 8th different ways. And sure, this would be 1 out of the 2 to the 8th different ways. But now I want you to visualize this from the perspective of what's the probability that within this outcome, right? What's the probability that within it this occurs? And so each of these trials are Bernoulli random variables. I have 2 options. And the probability of this occurring is 1/2 as well. And I have 1/2 to the 8th power. And the probability of this occurring as well is 1/2 to the 8th power, so on and so forth. Each of these events has 1/2 to the 8th power probability of occurring. And how many of them do I have? I have 8 choose 3. So what's the probability that I have 3 heads? It's going to be 8 choose 3, which also can be represented as 8 with the binomial coefficient symbol with the parentheses. So I can write this as 8 choose 3 multiplied by 1/2 to the 8th power. Does everyone see that? The probability of me rolling 3 heads, flipping 3 heads out of the 8 possibilities, 8 flips, is 8 choose 3 times 1/2 to the 8th power. So what do you guys think would be, what would be when you have the probability that the random variable equals 4? Or in other words, I have 4 heads out of the 8 flipping of coins. What would be this probability? So now think about having 8 heads. I mean, 3 heads instead of 4 heads instead of 3 heads. I would want to have 4 of those positions being right. Exactly. You see? Now you start to see that there's a structure behind, there's a pattern. And that's why random variables are very good, because if we wouldn't discuss about random variables in this manner, you would just go about finding the probabilities every single time. But there's a pattern, there's a structure behind it. So this will be 8 choose 4 times 1/2 to the 8th power. You see how we can generalize this now? So what's the probability that my random variable equals I? As you can tell, what's the only thing that changes? The probabilities of each of these events are all the same. They're equally likely. What changes though is the number of heads that I want. If I want 3 heads, this is 8 choose 3. If I want 4 heads, this is 8 choose 4. If I want 5 heads, it becomes 8 choose 5. If I want I heads, kind of weird to say, it would be what? It would be 8 choose I times 1/2 to the 8th power. And this will be the probability mass function. You guys see that? This is the probability mass function of this particular random variable defined by the number of heads that I get when I flip 8 times. Any questions about this example? This random variable, the binomial random variable. And I hope now you can see why it's called binomial, because I'm using binomial, what are called binomial coefficients, which is the combinations counting technique. Now, this may not be so, it's not complete. This example is not complete because the probability of flipping a heads or a tails is equally likely, right? So it's 1/2. So there's not much of a, you don't see the complete picture yet of the binomial random variable. But any questions about this? Everything good? Is that clear? Not clear, clear, not clear. Okay. And so note, if I take the sum of the probability that x equals I, as I goes from 0 to 8, this should equal 1. Because this represents, if I take the sum of all of these, right, this would represent the whole sample space. Yeah, it's gonna take some review. Yeah, that's okay, that's fine. This is the first introduction to it, so of course it's not gonna be clear as crystal. So how can we change this up a bit? I guess we can end with this here. So suppose there is a 30% chance of rain every day for the next 7 days. And I want to find the probability mass function for x. Now, how do we define x is up to you. We can say the success being that it rains or that it doesn't rain. So that's up to you. So we can say this, the number of days, x will be the number of days that it rains within a week. So you see how this is a binomial random variable? This is an experiment where a binomial random variable is represented. Each day, we're assuming, of course, where the assumption is that each day is independent of the previous day, which in reality it isn't, right? But each day, we're assuming that it's independent of the other day. And each day, the probability of it raining is the same. So if there's a 30% chance of rain, there's a 70% chance of no rain. See, we have 2 outcomes. What do you mean how x is? What I mean is that I can say x is the number of days that it doesn't rain within the week. That's what I mean by you can define x to be anything you like. Well, not anything you like, but it's not so rigid. It's not so static. It's not like, oh, this is only x can only be defined this way. No, I can say x is the number of days that it doesn't rain within the week, or x is the number of days that it does rain within the week. So there's more than one way of defining X. It's up to you in that regard. So I defined X to be the number of days that it rains within the week. So what's the probability? What's the different values for X? I can have the number of days that it rains to be 0, to be 1, to be 2 days of the week, 3 days, all the way to 7 days. So for example, what's the probability that I have 2 days that it rains? So what I could do again, right? I can do is what? So X, what is X equals 2? What does that represent in the sample space of this probability experiment? Well, I can say, hey, each slot represents a day. So I got 1, 2, 3, 4, 5, 6, 7. What's the probability? What's one configuration of having 2 days of it raining? Well, I can have the first 2 days rain, and then the next 5 days, no rain. I'm gonna call N being no rain. Right? Okay, now you guys are quick with it. Now, instead of me going through every single possible outcome, right? Instead of me saying, okay, I can have this day, first day rain, I can have the 4th day rain, and then everything in between, right? I don't want to know every single possible way. I just want to know how many of them are there. So instead of doing all of this, I can say, hey, there's 7 choose 2 ways, or in other words, 7 choose 2 ways of me getting two days that rain out of the 7 days. So I know there's 7 choose 2 of them. Now for each of these outcomes, what's the probability? Now, Ethan, be careful, Ethan. And we're gonna end with this. But be careful, Ethan. It's not 0.3 to the 7th power. It's not. You see, that's why the previous example was not complete. This is more of a complete, right? There's a possibility that it doesn't rain. What's the probability that it doesn't rain? It's 0.70. So if there's a 30% chance of rain, as we had in the beginning, right? Then that means that I'll do it with this one. The probability of this happening is, how many days does it rain? 2 days, right? And the probability of it raining is 0.30. So 0.3 is going to appear twice. And how many days doesn't it rain? 5. But what's the probability of it not raining? It's 1 minus the probability that it does rain, which is 0.7. But how many of them do we have? We have 5 of them. And the idea is that each of these outcomes have the same probability. How many of those outcomes do I have? I have 7 choose 2 of them. So what's the probability in an overall that I have 2 days out of the 7 days that it rains? Well, that probability is defined as 7 choose 2, 0.3 squared times 0.7 to the 5th power. So every binomial random variable has this form of the probability mass function, all of them, that constitute of having a number of trials occurring independent of one another, where each trial has 2 outcomes. We have some kind of structure like this: 7 choose 2 times 0.3 squared times 0.7 to the 5th power. Okay, so again, we're just beginning our journey into random variables. In particular, we're going to start with discrete, talk about the different kinds of discrete random variables, and then we'll talk about continuous random variables, and we're going to make progress that way.